Welcome to your system design topic all about NoSQL databases. This is going to be a fairly comprehensive introduction. So we're going to talk about what a NoSQL database is, how the data is structured, how things work behind the scenes, how they're different than relational databases, all kinds of good stuff in this video. Now, this is not a hands-on video. We are going to talk about some design for NoSQL databases, but if you're looking for some hands-on practice, you'll have to check out the upcoming lessons. But I will promise you that with this one video, you will finally have a detailed grasp on NoSQL databases. We will also be talking about some of the most common NoSQL databases by name, so you know where those databases fit in the NoSQL database world. So you won't just leave this video knowing some basic concepts, you'll know some of the most common databases and when you might want to use them. So I'm really excited about this video. I feel like the entire system design playlist has been building up to this moment right here. And I'm going to interrupt it with a message from our sponsor, which is my mentorship program. So if you're ready to seriously level up your skill and your career in software engineering, get a better grasp of back-end systems and designing applications, this mentorship program is for you. You don't have to come in with any prerequisite knowledge. We meet you where you are in terms of skill, build up a plan, a customized roadmap to get you to your goals. So it's a really great opportunity if you're ready to level up, put in the work, and get to that next level of skill. So I'll leave a link for that down below. Would highly encourage and appreciate you checking that out. Other than that, if you're not interested in the mentorship program, the least you can do for me is to subscribe because we're trying to get to 1 million subs. We're so close, we just have like 330,000 more to go. Not too many though, so we're on our way. So if you want to support this content, be sure to subscribe and share it with another person. So before we talk about NoSQL databases, NoSQL, which by the way stands for not only SQL, before we get into that, we should first talk about SQL databases. You might hear it as SQL. I generally say SQL, but really not a huge deal which one you say. So this stands for Structured Query Language. So Structured Query Language is a language standard for communicating to relational databases. So this is an important word. So relational, the word relation here refers to tables. Commonly, people will think that this refers to relationships between tables, but really the term relation just means a table. So this is a database that everything is stored in different tables. Now there are a bunch of different relational databases, but they all typically are built off of the SQL standard language. So working with them is pretty common. There might be a few variations between one database and another, but they're all pretty much built on this SQL standard. So that summarizes SQL. But let's talk about what it looks like to store data in tables before we talk about NoSQL. We're not going to get into a ton of detail, but we do want to make sure we have that foundation built. If you're already really comfortable with relational databases, then you can just, watch this to refresh your memory, and we'll get into NoSQL in just a second. A relational database will have tables, and a table can be visualized as columns and rows. So typically we'll have some column headers, such as ID, and then name. And then let's say this is an account for a website. We can just say if their account's verified or not. So we'll have an ID of 1, name Caleb, verified is true. We'll have another user 2, this will be John, verified is false. And another user 3, Sal, we'll say that she is verified. So these are rows. So we have 3 rows currently, each row having 3 columns. So you can see that it is a rectangle and every row has the same data. The data is very structured. So this follows a structure, or what you will often hear as a schema. In this situation, every single record or row has an ID, a name, and then a Boolean true or false. If we want to store certain information in a relational database, sometimes we'll split it across multiple tables. So let's say these are accounts for a website, and we also want to store devices for that user. So we could send push notifications, for example. We might have another table. So let's say this is the users table. We might have a devices table, and this might have a device ID. And then we'll have some way to refer back to the user table. So we could have a user ID, and then we'll just say device for simplicity here. So this will be the other table. And it's going to look something like this, where we might have a device ID 37, user IDs 2, and then device would be, I don't know, Samsung or whatever. Doesn't really matter what the data here is. The point is we have another table that points back to the original table. This here describes a relationship, and relationships build the entire structure of relational databases. You're going to have data split up across multiple tables. I've done a couple database design videos here on YouTube. You may have seen them. This is usually fine, and in fact, it's often recommended if you have data that nicely fits split up across multiple tables. You have a bunch of data and it's connected in some way. However, there are scenarios where this is not ideal, and this is where the NoSQL world comes in. And in this situation, you'll often not have multiple tables with relationships. You will have nested data in a single collection or table, and the way you design your data is a little bit different. In this example, you could imagine just taking the devices for a certain user and storing them with the user. So the data might look like this. The ID, in this case, we'll go with John, is 2. The name is John. Verified is false. And then we can have another devices attribute. And this could just be nested data. So we could have an array with the device information here. And this could be a simple string, or it could be an object itself. So here it could be a primitive, such as a string or a number, or it could be an object where we basically have this data in a similar structure, just now inside of this nested array that's associated with this devices key. So this is pretty similar to what you might see with JSON or objects in programming languages. So JSON, this is one example of how you could represent data without having to have multiple tables. But even in the scenario where the data you're working with is like this, and this is what it looks like when you're building the application, you still might split this out into individual tables at the database level. So there's a disconnect between the way we work with the data in the application and the way it's stored in the database. And this layer is where you write SQL, or you use some kind of object relational mapper, kind of getting into the details there. But the point is, the way we work with the data is not always the same as how it's represented in the database. But with a NoSQL database, we could actually store it in the database like this instead of splitting it up across tables. And now all of the information about John is together as a single unit. Let's go through another quick example of this where this is going to be really handy. Say you have some course website and you're going through the lessons. We have lesson 1, and then we might have like a video player for it. And you can just imagine this being displayed on a website. Maybe we have some notes for the video, or maybe some downloads. That's a paperclip, like an attachment. It looks nothing like a download, but you get the point. Lesson 3, we might have some kind of quiz or some information that's perhaps a little bit different than these other lessons. And also, as we're viewing this, we might get some additional information on the side, such as the author bio, maybe a picture of them. So some information about the course. And you can imagine all of this information, while it's being viewed together, is actually stored in a bunch of different tables in the database. So we might have a course table, an associated lesson table, an attachments table for downloads. We might have quizzes, and basically we have a bunch of information spread out across a bunch of tables. But when we are actually accessing the information on the web page, it's all brought together in a single location. So you can think of this almost as a single unit, where this is kind of like a snapshot of the course. So the question is, if we always access this information together, why do we then store it spread out in different tables? Wouldn't it just make sense to store it all in a single object in the database? And sometimes it does make sense to do this, putting it all together in the database. Other times it does not make sense to do it, putting it all together in a database. If you have a bunch of different structures and you need to access those structures in arbitrary ways, maybe you need to grab all of the quizzes or all of the comments for the lessons, or do some arbitrary queries where you don't know those queries ahead of time, then it might not make sense to put everything together. But there are scenarios where it does make sense to put everything together. And in this scenario, we can basically store all of this information in a single object that then goes into the database. So this could be stored as a single unit into the database. So what is accessed together is stored together. Accessed together, stored together. Now, I mentioned that sometimes it makes sense to do this, sometimes it doesn't. That's a design decision. You will have a stronger intuition of when you should do something like this, where you put it all together, and when you should not by the end of this video. But it's still something that's going to depend a lot on the application. We'll get into some of the details of choosing a relational database over a NoSQL database, and it often comes down to how the data is accessed and the scale of the application. I want you now to build a stronger intuition and understanding of why people say NoSQL might be more scalable. This is usually only important if you get to a scale where you have to do data sharding. We've talked about sharding earlier on in this playlist, and I'll draw a quick scenario of that. So assume we are working with a relational database. We might have a few nodes split up. So each one of these is a database instance, but they work together as a unit. If we're working with a relational database and we split this data up across different nodes, where every node doesn't have the full data set, just a portion of the data set, that's the idea behind sharding. The problem is that we might access one course, but we end up having to retrieve information from 3 different nodes or multiple nodes across the world. So the benefits of sharding are lost. We basically split up the data so that we can have a higher throughput. But now to read that data, which is split up across multiple nodes, we then have to access multiple nodes. So we've lost the benefit of splitting it up in the first place. I have no idea what's going on here, but the idea is we have to access multiple nodes to build this individual page. Switching over now to NoSQL, everything that is accessed together is stored together. So that means even if we have a cluster of, say, 3 nodes, all of this information is going to be accessed from just a single node. Because if you access just a piece of the information, it all comes together. It's stored as a single unit. So we don't have to then go and access these other nodes, which is obviously going to be better. So that's one of the first benefits of NoSQL is the scalability. And I'm not just trying to throw around database buzzwords saying you need to get a NoSQL database. I'm just trying to help you understand why people say NoSQL databases are potentially more scalable. It's because the data that is used together is stored together. So NoSQL databases are typically cluster friendly, and specifically talking about multi-master write and read nodes, not just read replication, which is a bit of a different solution and doesn't actually increase the write throughput of a system. So this is for both write and reads. The next major benefit, which has some drawbacks we're going to get into, is that NoSQL databases are often schemaless. So let me write up here some example data, and then I'll talk about what it means to be schemaless. So here we have one object where we have a user ID, a name, and an email. We could also have in here nested data, so we could have the devices, which is an array of device objects. But I don't feel like writing all that out, so this is what you get. The idea of this being schemaless is that this is one example of a user, but we could have another user that follows a different schema. So in this situation, we have another user here that instead of having an email, they have a phone number. But here's the important thing. It's not so much that this will have an email and it's just empty, and this will have a phone number and it's just empty. That would be the case for a table because we have to fill in every value. In this situation, because the attributes are actually associated with the values in the object, we could just remove an attribute altogether. So we don't have the email in here at all. It's not empty, it's not none, it's not null, it's just not there. Same thing up here, we don't have a phone number at all. So it's hard to actually write this in table form because every individual record could have different values. However, it's often the case that you could attempt to do this and get like a close representation of what it might look like, even though it might not accurately represent how it's stored on the computer. But if we wanted to do that, it might look something like this, where we have an ID, and I'm just going to call this ID just to keep it shorter, a name, an email, and a phone. The first row will have values for the first three. The next row will have values for the ID, name, and phone, but these would just be empty. This is how you could represent it in a table, even if that's not how it's actually stored. So sometimes, even with the NoSQL databases, they will give you some kind of table representation, but we're not just storing a bunch of empty values, we're just not storing values for those at all. So the database being schemaless can be a good thing, it can be a bad thing. Let's talk about some of the pros and cons. If you're prototyping some software, you're trying to build quickly, a schemaless database makes it 1,000 times easier. Basically, you just write how things should look in the software and you store it in the database. It does not complain. Meaning if you wanted to add a new attribute, you just add in the new attribute. You don't have to worry about updating all of the previous records by adding a column as you would have to do in a relational database. This allows people to very easily work through their application, prototyping, adding data, changing data, not having to think of the exact data structure up front. The big downside to this is that you're kind of pushing certain problems down the road and they might come back to bite you. So if you're drawing a web page and you're trying to present data that comes from the database, now if you're unsure if that data is going to be there because it's a schemaless design, you have to conditionally render the possible attributes because there's a chance that attribute might not be there, or there's a chance different attributes might be there. So we're basically removing the static typing of the database, and now we have to dynamically consider all of the possibilities at the application level. Because even if a database is schemaless, there's still an implicit schema. Data will generally follow some structure, and that's how you decide what to display on a web page. So if your data is all over the place and you're not following some schema, the amount of work you're going to have to do at the application level goes up. So no schema over here means an increase of work on the application to be careful to not mess anything up. You don't want the web page to say undefined or something weird being displayed, or you don't want to throw any exceptions trying to access data that's not there. So those are the major pros and cons. I think people assume, oh, it's schemaless, it's going to be easier, but really they're just putting the work at the application level, and later on they're not going to have as much trust in the database because there's not an enforced schema. Compare this to a scenario where we do have a schema and we label columns that are never supposed to be empty as not null. We're working with a backend language that's statically typed, meaning we know the types of the data we're expecting at compile time. Then overall, the amount of work is going to go down at the application level. There might be a little bit more thinking at the database level, so you might need to plan ahead a little bit. So the more planning and the more prep you can do here, the less issues you can have down the road. That being said, there are scenarios where things being schemaless makes your life a lot easier. Consider the case where you have a web page and maybe you have some custom modules in here that the user can put on the screen. Maybe it's a dashboard with different data, or maybe they can plug in their own modules with some custom plugins. In this situation, it might be very handy to go for something schemaless because we don't necessarily know all the data structure that's going to be used for all of these different modules. You might have to think a lot ahead of time to think of every possible scenario, or you might have to continually update possible scenarios back in the database. Sounds like a pain in the butt. Hey, maybe we could just go schemaless and let that be a little bit more fluid there. However, this doesn't mean you have to use a NoSQL database, because a lot of the relational databases have introduced a schemaless component, which is basically to store JSON in a column. So you might have a table for widgets where you have a widget ID and then the widget data. And the data type for this is JSON, which does give you that flexibility, but still within a database table. So just if you want some schemaless, but you don't really want a full NoSQL database, that's totally possible within a relational database, and is probably what I would first recommend versus jumping ship and going straight to a NoSQL database. The other major thing that I would be aware of is that the design is often query driven. So instead of asking, how do I store this data, you might ask, how will I access this data? So the relational databases are often pretty good at just doing arbitrary queries, joining from whatever tables you need, very, very flexible. Whereas it's often the case with NoSQL databases, you have to think ahead on what queries you're going to be using to access that data, because the storage is a little bit more strict on what's possible for the queries. Now, that's not always the case, especially with NoSQL, because there are tons of different databases within the NoSQL category. But a quick example of this would say, hey, you have to access by the key or by some index, and you can't do any arbitrary queries. That might not be 100% the case for the database you choose, but that's a way to think about it, where you have to think about what the queries are going to be ahead of time. And if you need to change that, then you might need to add in an index or change things a little bit. So there's less rules like normalization and things like that with NoSQL, but there are more design decisions about how you'll access the data. And you'll become more familiar with that and become better at it as time goes on. All right, so at this point, we have a pretty good foundational knowledge of NoSQL, how it's different than SQL, relational versus non-relational databases. You might also hear structured versus unstructured. Now I want to talk about some of the different types of NoSQL databases. Because it's a large category, there are a bunch of different types. So we'll talk about some of the main ones. There's probably others out there, but this will cover most of NoSQL. So I'm going to put 4 up here. The first is key value. And I'm just going to write all of them up here so you can know what we're going to be talking about. The second is document databases. The third is wide column. And then the fourth here is graph databases. And there's probably a couple others, like maybe you could say time series databases, databases specifically used for working with events in time, or maybe search specific NoSQL databases, ideal for searching through large data sets. There's probably a bunch of other variations, but this is going to get you the majority of scenarios. So let's do a quick overview, and then I will erase and we'll go into the details of each of these. So key value, document, wide column, these are all relatively similar, where you'll have some key with some associated data. So for key value, you can just imagine literally having a simple key for accessing the data, and then an associated value, which can be quite complex, such as an object. Document database is going to be pretty similar, but it might have more insight into this value. Instead of just being like a snapshot of some data, you might be able to query certain things within that value. Wide column, you can imagine a relational database where you have rows and columns. The difference here, though, is that instead of every row having the same columns exactly, a wide column, you can have certain columns for certain rows, and each row can have its own set of columns. And then lastly, graph databases, you can visualize a graph as nodes and the connection between nodes. So these are great for analyzing connections between data. So you can imagine social networks or things like that. So that's the high-level overview. Probably didn't give you enough detail, but I just wanted to show you what we're going to talk about. Now we're going to rewind, talk about it in a little bit more detail. So let's talk about key value databases. To understand this database best, you should first understand hash maps. A hash map is a data structure that has a key with an associated value. And the key is actually used to determine the storage location here. So typically this will be processed through a hash function. And I don't know if we've talked about hash functions yet in this series, but basically it's a function that takes an input and gives out a consistent length output. We can go into the details of the different types of hash functions, how they work, but the idea is it can take any input and give out a consistent length output. The same input will give you the same output. So we have this hashing function, and basically we'll take the key, put it through that function, and use this output to determine where the data is actually stored. So it seems kind of complex if you're not familiar with this. The reason why we do this is because it allows us to very quickly access data by a key. So let's say we did this with the key 5. We would go through this process. We would hash 5, take that output, and then use that somehow to decide where that data is stored. Next time, when we want to access 5, so not actually insert the data, but actually retrieve that data, we would just go through that same process. We would process it through the hash function, figure out what that output is, and then use that to retrieve the exact location for the associated value. So to repeat, the key is the basically primary key used to identify the data, but also the storage location is derived from that key through this hashing process. So we know exactly where that data is stored on disk or in memory in the case of a data structure like a hash map. When we take this idea and bring it to a database, now the storage is on disk. So we can go from key to exact value on disk in constant time. So it's a very, very quick operation because we don't have to search through any data. We just process it through the hash. It gives us the location. That's all done for you probably automatically. This is just how hash maps work, and key value databases are built on the ideas of hash maps. So if you've used dictionaries or associative arrays, you're using hash maps. Now you can just imagine instead of storing that data in memory, you're just going to store it on disk. And boom, you have a key value database. Or in certain scenarios, that data won't even be stored on disk. So a popular example of this is Redis. Redis is an in-memory cache, and this will allow you to basically put a layer between the database and the application for commonly accessed data. So Redis is my go-to when I'm thinking of key value data stores, but there are plenty of other ones out there. So another one that you could look into would be DynamoDB. Now, the thing to remember with key value databases as a general rule is that the value is seen as a single unit. You can just think of it as a box that contains all the data you need. The database is not intelligently aware of what's going on in this box. You just give it a key, it gives you back the thing at that key's destination. Let's say this object that we were retrieving was a video on a website, and then we had a comments, and this comments might be a nested collection of a bunch of data. This is something where you're interacting a couple of layers in. You're not probably going to have a bunch of capabilities with the key value database to manipulate deeply into the nested data. Typically, you're just going to work with it as a snapshot, then work with that data in your application, and then store the data back in the database if you wanted to do an update. And most likely, even if you did work with some attribute in the bigger object, the bigger object is going to be accessed anyways, so you're probably not going to save any write or read throughput by working at a layer in of the nested object. Hopefully I'm not getting too abstract here. It's hard to go through this without hands-on examples. Hope to release some of those here soon, so be sure to subscribe. But for now, the idea here is that you should think of the value just as a snapshot of some data. You then work with it at the app level instead of doing a bunch of complex operations for certain attributes in that value. So now let's talk about document databases. This is very similar in idea, but now you have a little bit more understanding of what the associated value is. So these databases are much better for working with that nested data and that value being maybe a couple of layers deep. So big examples of this would be MongoDB. I think CouchDB would be another good example. And I'm sure the cloud providers out there have some of their own document databases. So there's probably more to this list, but when I think of document databases, MongoDB is what comes to my mind. This is a database where you can just access data by its ID, but it also gives you a very strong query language where you can access nested data and manipulate a couple of layers in. So the knowledge of the actual value associated with the key is much stronger. So you could say that the value is transparent and the document database has knowledge of what's in that value and could potentially even index nested data. So if you're looking for that key value like experience, but you want to have complex control over the actual object, the document, then a document database makes sense for you. Next up, we have wide column databases. And I wanted to make sure I clarify that this is different than a column-oriented database, which is pretty common in any kind of data warehousing applications. So if we basically took a relational database and instead of organizing data on disk by row, we organized it by column. So instead of getting all of the data for one particular order together, you might get all of the total order amounts. And because this column is stored together on disk, we can very easily do analytics with that data. It's pre-organized for convenient analytical processing. So if you've heard of like OLAP, online analytical processing, compared to OLTP, online transactional processing. So this is a column-oriented database, data warehouse. This is not what we're talking about here. We're talking about NoSQL, wide column data store. And in this situation, you're still going to have rows. And for any row, you'll have dedicated columns with values. So it might look something like this. But the difference here is between one row and the other, you can have different columns. So you might store one thing for a certain row and store something else for another row. The benefit here is that a column value is only written if there's a value for it, compared to a relational database where every single row is going to have something for that column, even if it's just going to be null. So when we're talking wide column databases, you're probably going to hear Google Bigtable, as well as Apache Cassandra. These are really the defining databases. You can check out the white papers for these. Okay, I don't really like white papers. They kind of put me to sleep, not gonna lie. But there's actually some good stuff in some of these white papers about databases. I use dark mode, so it's not even a white paper anymore. Much better for your eyes, by the way. Apache Cassandra is really cool because as you scale, instead of having a massive, really powerful, vertically scaled database instance, Apache Cassandra is designed to go horizontal with commodity hardware. So it's perfectly able to run the database across many smaller, weaker nodes. And these are all connected in the database cluster. So that's where Apache Cassandra really shines. And the number of nodes you can have in one of these clusters is insane. I don't know what the highest Apache Cassandra cluster has been, but I've heard of clusters being in the tens of thousands of nodes, all working together to store data to support some system. So that's pretty wild. I also wanted to mention HBase. This is kind of like Google Bigtable, but in the Hadoop ecosystem. So if you know anything about that, you might be familiar with HBase. And then I also wanted to mention ScyllaDB, which is basically Apache Cassandra, Java, rewritten in C++. Now, if you're doing additional research on NoSQL on the internet, you'll probably find some written stuff and some videos by Martin Fowler. Great stuff about NoSQL databases. He categorizes these three as aggregate databases. So what is an aggregate? You can think of it as a logical single unit of information. It's what we are trying to store and work with. So in these three databases so far, you will basically store, going back to what I was saying, everything that's accessed together on disk. So on his website, he gives the example of an order with the line items. Even though these are logically two different things and would be split up into two tables probably in a relational database, when we're talking about aggregates, the thing we're trying to discuss here is the order. So this is going to be considered a single unit, an aggregate in this scenario. So you read and write aggregates. And in general, you want to avoid operations that go outside of the aggregate boundary, because then you have data integrity risks unless you have some kind of transaction mechanism. But updates to a single aggregate are atomic, so you can basically do anything with that object, store it back on disk, and you can rest assured that the full thing is going to be saved at once. Now, graph databases were excluded because that has data split up across these relationships. It's kind of like a relational database, but instead it's split up as a graph. We're not going to talk a ton on graph databases. We might do some dedicated content to it later down the road. But for now, you just need to understand that a graph database stores things as a graph where data is stored in nodes and they are connected, Neo4j is the biggest example of a graph database if you want to get some practical hands-on experience. Now, I wanted to briefly mention something that you should be aware of when we're talking about NoSQL databases, and that is the idea of a replication factor, as well as the concept of consistent hashing. We're not going to get into the details of that in this lesson, but this is a very common system design problem, so it's probably worth doing additional research on it. So we'll likely talk about this in a dedicated lesson coming soon. But for now, let's just get the high-level overview. Basically, since we are in a database system that splits the data up across multiple nodes, we need to be careful that one node doesn't go out and we lose a portion of our data. So consider a system where we have a couple of different database nodes, and these are all connected in a database cluster, and any of the nodes can write or read data. So there's not just read replication, you can write to any one of these. However, it's likely the case you won't just write to one, you'll actually write to a few. So you might start by writing to this one, and then that data is replicated by the database to the next nodes. So you don't just have the data in one location. That's a single point of failure for that data. So we want to replicate it. We have some data redundancy in that case, and our data is much safer. Same idea when we read data, you might actually read from multiple nodes. So you could read from both of these nodes, confirming that the data exists on both of these nodes, helping ensure that we get the most up-to-date data. In this scenario, there are 3 values that you should consider important. The first being the replication factor. The next is the number of write acknowledgements, and then the next is the number of read acknowledgements. So I'll go through an example. Again, you don't have to understand all the details of this because we're going to do a dedicated lesson on it, but consider an RF of 3. What this means is that data is replicated to 3 nodes in the cluster, not every single node. Consider the case where you might have a cluster of thousands of nodes. You don't put that data on every single node. So a replication factor of 3 would mean that when we write to a database instance, that data ultimately will be replicated to 3 nodes total. The W here is how many we have to actually confirm have a successful write before we consider the write to be a success. So consider the case where W is 2. We might write to this node and this node before we say, hey, the write was a success. The read, similar idea, we might read from 2 nodes to confirm that the read was a success. So we read from this node, for example, and this node, for example. With data replication, that might be eventually consistent. So something that's replicated from one node to the other will take some amount of time. So because that write number is lower than the actual replication count, it might not replicate to all of the RF nodes immediately. It only needs to write to 2 of them for that operation to be considered successful. The rest would be replicated afterwards. So then the question is, when we're reading, how are we sure that we're getting the most up-to-date data? And the formula for this is if the write acknowledgements plus the number of read acknowledgements is greater than the replication factor, then we should get consistent data. Because in that situation, there's a guaranteed node overlap in that set of replication factor nodes. So in this situation, we write to 2, and then we read from 2, and you can see there's an overlap right here. So if we write to 2 and then immediately read from 2, we're sure that we're going to get the most up-to-date data because at least one of the nodes has the newest data. However, if you don't need these requirements, you could of course lower these numbers. So we could say R is 1. In that situation, we might read from a node that does not have the most up-to-date data. But if we don't need it to have the most up-to-date data, this is going to be a faster operation. So this is going to ultimately reduce latency, and it's a trade-off between consistency and latency. Now there's also the concept of a coordinator. So we make a request, maybe we hit this node. This node acts as a coordinator, directing the request to the correct location where that data is stored. But this brings up another question. How do we know which node the data is stored in? If we're given a bunch of nodes and we say, hey, find the associated value for this key, how do we know where to access it? So that's another question we're going to talk about, and this has to do with some kind of algorithm to find the correct node. Typically, it's going to be consistent hashing. So we'll talk about what that means now. This whole thing is called Quorum Consensus, And this is basically a system for multiple nodes to work together to give the correct data. So they all have to be using the same consensus mechanism. So that's what these parameters help define. Now I want to briefly talk about the idea of consistent hashing. Let me bring back our database cluster, and we'll draw these in a ring. So you can just imagine a circle, and that's a pretty bad circle. But if you remember back to when we had the hash map data structure, we had a key and a value. And when we were just working with memory, the key was used to determine the memory location. It's going to work very similar here, but now instead of some location in memory, it's going to be some location in this database cluster. So the way we get that position is the key goes through some kind of hash function. So let's go through an example data just so this can be a little bit more concrete. Let's say the key is 123, and this has my user data, so username, Caleb, and so forth. We take this key, process it through a hash function. This gives us a hash value, and that hash value can be represented as a number somewhere between 0 and whatever the max value is, depending on the hash function. That's kind of irrelevant. The point is, it gives us some number back that can be used to determine the location. So let's just say this circle represents the full range of values. We'll say it starts right here. This is 0. And for simplicity, this is going to be 100. This will be 200. Right here will be 300. And here will be 400. And then let's say we process our key through this hash function and we get 255. And I know you might be thinking, well, why don't we just use this key here? Well, this doesn't have to be just a simple number. Basically, we need to take some key, process it through to get some number that we can then use to determine its location. So where would 255 go on this ring? Somewhere about right here, 255. And then by convention, we basically just put it on the server right here. So it's within this range, so it goes on the server clockwise on this ring. So basically, in one quick operation, we just take the key, hash it, get the hash value. That tells us exactly which server that data will be stored on. Then going to the replication factor thing, it's going to be replicated to a couple more nodes. So given this information, if you can even interpret my handwriting, given this key, can you tell me how you would find that information to read that information, not to make a write? It's going to be the same exact process. So we do a query for ID 123. Behind the scenes, that gets processed through the hash function. It'll give us the same value. That's a critical part of the hash function. The same input needs to give the same output, which is true for hash functions. So we then can immediately jump to the correct location in this database cluster. There still might be like a coordination node. So for example, we might make the initial request to say this node, saying we're trying to access key 123. And then this node can do the magic calculation stuff and say, oh yeah, here's exactly where you need to go to get that data. Otherwise, if we didn't have this coordination node, then we would need some external system to figure out which node to get the data from. So there might still be some routing going on, but it's a very quick operation. Well, that's the overview of consistent hashing. I kind of ruined all the fun because now the next video on these topics, you'll be like, I already know all this stuff, but we might be able to go into some more depth. I feel like having a high-level understanding of these topics is good to know for NoSQL, but I don't really feel like you have to know the inner details of everything in order for you to understand NoSQL in general and use it as a developer. So I'm trying to just give you a little bit here so you have an idea, but if we really want to go into the details, that would make sense to do in a dedicated lesson. Now let's talk about another challenge with NoSQL databases. So we have the data distributed across multiple nodes, as we've seen, but we have to give some kind of ID to identify how to find that information in the database cluster. So in the previous example, I used the key 123. This ID has to come from somewhere. Now, if you're coming from a relational database system, you're probably familiar with some kind of auto increment or equivalent. So this is not always a native feature in NoSQL databases because of the distributed nature of NoSQL. Just consider the smallest example of this. If we have two nodes, and let's say the last used ID was 1, 2, 3, but the data is split up across these nodes. So the highest on this one might be 1, 2, 3, and maybe it has had the last few writes. So it might have 1, 2, 2, 1, 2, 1. And this one, the most latest, might be 120. So then let's say we write something to this node. What ID do we use? Because this node currently does not know that 123 exists over here on this node, right? So it's not just going to naturally know to use 124 unless these are sharing some kind of coordinator node to distribute IDs. So that's one possible solution. You basically have an ID distributor, and this will basically take a request and give back an ID for this auto increment feature. So we basically just have a centralized ID creator. So when we have an external ID generator, we now have to basically move that ID generation outside of the database. So often with NoSQL databases, you will be responsible at the application level to give an ID. So we have a database node and we're inserting data. The insert is going to have the ID already. So this comes from the application, not from the database. So that means our application can communicate to that centralized ID server. Now, there's problems to this because now we have a single point of failure. We built a distributed database and we're relying on a centralized service. So you might do something where we actually load balance this and we have two ID servers. And then maybe this one distributes odds, this one distributes evens. There are various solutions, I'm sure. But the main thing you need to understand here is that it's no longer the database's job to generate the ID, it's the application's job. So the ID is decided here, not here. And that means anything you can do at the application level to generate an ID could potentially be a valid solution to this problem. So we've talked about one, which is a centralized auto increment. Kind of complex. Probably wouldn't want to do this if I was just building some system and I wanted to use a NoSQL database. So there are a couple of other really good options. The next option would be to use some kind of natural key. So a natural key is great here because it's associated with the data that's being inserted, so you don't have to use any external resources. So that's a great option, and that won't require an external system. You can do that all within the application that has the data you're working with right there. The third option would be to generate something random at the application level that's not auto-incremented. So a UUID, or you might hear GUID, universally unique identifier and globally unique identifier. Same idea. Basically, this is just a 128-bit value that can uniquely identify any data, because with 128 bits, the value is large enough that the chances of collision is extremely low. So this is great, but the downside here is it's not searchable very easily. If you're trying to access a value and you have the ID already, this is going to work great because you can just access that exact ID, no problem. But if you need to search through the data, there's no logical sorting because the IDs are random. So that's the big downside here, as well as every single key taking up 128 bits. Even if you're working with really small amounts of data, every single one is going to use that full bit size. The fourth solution, which is a little bit more complicated in terms of understanding, but this is pretty common for different services out there, is to use a snowflake. And this is a 64-bit value that's not random, but actually has some encoded information in that value. So something like 1 bit is a sign bit that's reserved. I think there's 41 bits to a timestamp that actually indicates when the ID was created. 10 bits to the system ID, so whatever server is creating the Snowflake ID to avoid conflicts across servers. And then a 12-bit sequence ID, which is an auto-incrementing value that resets every millisecond, so you can create a lot of values every millisecond. So all those put together will be 64-bit, but the value means so much more than just a 128-bit randomly generated number. So this is something you'll see for large applications that want to have some identifying information inside of the ID, and they're going through additional effort to save space and that information is sortable because there's a timestamp. So there are some really good benefits to the Snowflake idea, but it does take a little bit of additional understanding. We might do some dedicated content on that. Now to wrap things up, I wanted to go through 2 examples. So talking about how you might design something in NoSQL. So let's first start talking about a video system. So we're creating some video platform and we have a way for users to create comments. So I wanted to talk about this example because this is going to introduce some interesting things about keys as well as secondary indexes, which are very important in NoSQL. So again, thinking ahead of what types of queries we might be making. So let's talk about what a comment might look like. We might have the video ID, a timestamp. We're not going to be using the snowflakes or any IDs with timestamps embedded in them. So we're just going to have a video ID, which we'll just assume is a UUID that was generated, nothing too fancy. So we'll have a separate timestamp value. And then we'll have a user ID. This is who posted the comment. And then we'll have the actual content of the comment. So initially, there's going to be some challenges here because we don't have relationships. So this user ID, this video ID, it does not connect to another table with some kind of foreign key constraint. So if we want to have that connection, we have to do it at the application level. Basically, we have an app here. This accesses 2 tables from the database, or maybe 3. Users, comments, and videos. And then we do whatever we need with these 3 individual sets of data at the application level. So you just got to be more careful with data integrity. If the NoSQL system has some form of transactions across tables, you might want to use those for certain scenarios. But the idea here is that this user ID and this video ID are just values. They're not foreign keys to some other tables. And that's a big difference inside of NoSQL compared to a relational database. This first attribute here is often going to be called the partition key. And notice how we don't have a comment ID here. This might seem strange, but we have to think about how we are accessing the data. In this aggregate-oriented style of database design, we would access the video, and then we need to get all of the associated comments. So by setting the video ID as the partition key in the comments, we can access all of the comments for a particular video ID very easily. So if we had a comment ID, it could be here, but it wouldn't be the primary key of the table. It would just be another attribute. So we basically are going to group things by video ID, and that's the idea of a partition key. So things that are accessed together are going to be stored together on the same partition. So I'm going to remove that comment ID, but we have another problem here. We still need a primary key, which is unique. If we made it just the video ID, that's not going to work because we have multiple comments per video. So we actually need to use a composite primary key, which will consist of 2 values. So that's going to be the partition key plus this here, which is often called the sort key. Or you might hear it as the clustering key. And when you hear clustering here, if you're familiar from relational databases, the idea of a clustered index, it determines the sort of the data. This determines the order in which that data is stored. So these 2 combined can be our primary key. So we will not have any duplicate values where we have the same video ID with the same timestamp. So this helps us understand the basics of how we would structure a table in a NoSQL database. Now let's talk about secondary indexes. This is very important if you want to access the data from a different perspective, such as all the comments from a certain user. So right now it's highly inefficient because the data is stored by video ID and timestamp. We would have to do a table scan to get all of the comments with a certain ID. So we would add an index here. And you can imagine this index basically taking the original structure of the data and reorganizing it by a different key. So now we have the ability to retrieve by video ID, and we also have the ability to retrieve by user ID. However, this would obviously lead you to believe that there's additional work happening here. So anytime you add an index, that index needs maintained. You're basically putting that data in 2 different arrangements. So think clearly about what queries you really need so you can create those secondary indexes, but if you're not using one of them, then it's not really a good idea to keep them around just in case. You could always add an index later with some upfront work, but the idea here is we think ahead about what queries we might be making against our data. Now, one more quick comment about the information that I just erased is if we have some ID that has a timestamp or some kind of sort embedded in it, then we might not need a dedicated timestamp for the clustering key. So for example, if we were using snowflakes, in that situation, we could just use the comment ID as the clustering key or the sort key instead. So it might look like this: video ID and then comment ID. This would be our primary key. We could organize by video. That's how the information would be accessed. We want the comments for a certain video. And then this being an ID that has some sort information embedded in it can be used to sort the data from newest to oldest or whatever you need. This is basically the replacement for the timestamp if the IDs have that timestamp information embedded in them. So there's definitely benefits of using something like a snowflake. So I actually wanted to do a second example of Discord and a popular article online on how Discord stores billions of messages, recently updated to how they store trillions of messages. They use snowflakes in their system, and their primary key looks like this: channel ID, message ID. So very similar situation here where we have some channel, let's just say it's general, and we want to get all of the messages for that channel. So that's why this is the partition key. But we don't just want the messages thrown in there, we want them to be sorted in some way. So this secondary part of the key is a clustering key that determines the sort, and this is a snowflake. I believe this would be a snowflake as well. It's just not used for the sorting in this scenario. So we take the message IDs, we can retrieve the timestamp information from within the snowflake to then give a sort from newest at the bottom, scrolling up to the oldest. So that's a really quick overview of Discord's ID architecture. They used Cassandra, they switched to ScyllaDB, and now if you go read those articles, you'll have a pretty good foundational knowledge to understand what they're talking about and why it works for them. I've given a lot of information in this video, and this of course is not going to apply universally to all NoSQL database types. So definitely do your research for the individual database you might be working with. This is really just designed to give you that really good foundation. You should now be able to go into NoSQL databases with some level of confidence, as well as having more confidence going into any of the white papers, understanding what they're talking about with consistent hashing and things like that. So the final summary here is, how do you choose between a NoSQL database and a relational database? Hopefully you have a good understanding of that answer by now. Ultimately, it depends. So hopefully that helps. One thing I would consider doing though is wrapping your database in a very easy to consume API or SDK. So you can imagine having your database here and then wrapping this so that it's super easy to interact with based on the most common things you need to do. So for example, get users. This could be a function call if you're working with the database directly in your application, or you could actually just expose different API endpoints such as get users, post a user, basically writing out all of the different interaction points, the interface to the database, so that in theory, while it's not as easy in practice, you could take out the database, substitute it in for something else. So you could even switch between SQL and NoSQL, but the applications that interact with this interface have the same interface and do not have to change any of their code, because they're still going to get users structured just how they would expect, and you can do any transformation logic or anything you need to do here inside of the data layer. So whether that's through an API or an SDK or however you want to do it, basically adding some interface to separate the consumption of the database from the database itself can be very handy for creating scalable systems so that you don't break all of the interacting applications if you switch from one database to another. So if that doesn't make sense, you can imagine you have a bunch of different microservices, and all of these ultimately talk to the database. Starting out, you might use the exact database drivers that you're working with. So imagine you're working with some NoSQL database and you're writing direct for that database in all of these individual applications. But then you want to switch it out. You now have to go into all of these different applications, updating that code, which could be a disaster and make it pretty much impossible to switch out a database or to do any major changes like that. So while I don't love abstraction for abstraction's sake, just making things complicated, I do like the idea of abstracting away the database itself and just giving a nice interface. So in that situation, all of these apps would only talk to this outer layer. In this case, I'd probably make it an API so that we could do very easy cross-app communication. They just hit the API, get the data they need. They don't care what the database is or where the data is stored. They just know that if they hit the API, they get the data and they can use it in their app. So that's one specific example. You could probably structure it differently, but that's just an overview of an approach that you could use to basically reduce the possibilities of things going south if you need to make a change at the data layer. If you've made it this far, you are a legend. I have to say thank you, and I would really appreciate a subscribe to the channel if you enjoy this type of content. Again, check out the mentorship program. I'll have links for that down below. Go through that if you really want to level up your software engineering game. So that's the only two asks I have for you. Subscribe, check out the mentorship program, and I'll see you next time. If you have any suggestions on additional content or things you would like to hear about in more detail, let me know. Drop a comment, would really appreciate it.